Solids of revolution, the disk method. Take a minute to clear your mind and imagine revolving the shaded region around the x-axis. Try to visualize what this three-dimensional solid will look like. So we're taking this region here, extending from 0 to 2, and rotating it around the x-axis. Imagine what that three-dimensional solid will look like. Is this the figure you imagined? Notice that the shape of the cross-section is a circle. So here at this x value, we can see that a cross-section would be a perfect circle, and notice that its radius, r, would extend from the x-axis to the function y equals x squared. Let's go ahead and generalize this. Volume of a solid of revolution, the disk method, cross-sections perpendicular to the x-axis. If f of x is continuous and f of x is greater than or equal to 0 on the interval from a to b, then the volume obtained by revolving the region under the graph about the x-axis is given by, so here the volume is still going to be equal to the integral from a to b of the area function in terms of x dx. But the area is going to end up looking like a circle. So if we take a region that's above the x-axis and continuous, and we think about rotating it around the x-axis, the cross-section will look like a circle. So the area of a circle is pi times the radius squared. So the radius needs to be a function of x. So here, this is going to be my r of x. So notice that it's obtained by doing top minus bottom. So the top function is f of x, and the bottom is the x-axis, which is just y equals 0. So the radius r of x is top minus bottom, or f of x minus 0. So we have that the integral from a to b of pi times f of x squared dx gives us the volume of a solid of revolution using this disk method. So this will yield the volume of this solid. So r of x is the radius of the circular cross-section at different values of x. In this example, let's find the volume V found by revolving the region bounded by the x-axis, y equals x squared plus 1, x equals negative 1, and x equals 1 about the x-axis. So we'll start by constructing the region we're going to revolve. So we have x squared plus 1, so we have this parabola that shifted up 1 unit, and we also have the vertical lines at 1 and negative 1. Oops, so I missed a little bit. And we have bounded by the x-axis as well. So the region that we're rotating is this region here. And I would always recommend sketching the region, and if you have one, using a highlighter to highlight the region that we're rotating. So we're rotating this region around the x-axis, so I like to use a little circular arrow to indicate what line we're rotating around. So now the cross-sections are going to look like circles. So we can still think about constructing a cross-section as some generic x. So the cross-section would look like a circle when we revolve around the x-axis. And that radius would be top minus bottom, so this top function here was x squared plus 1, and the bottom function here is just y equals 0. So let's go ahead and set up and then find the volume. So we're going to set up the integral. The volume is x equals negative 1 to x equals 1, so we can see those are the x values my region extends from. And then we're going to have pi times the radius squared dx. So the radius, as we said, this is r, is top minus bottom, so just x squared plus 1 minus 0, or just x squared plus 1. So this is going to give us our volume, so now we'll go ahead and evaluate this definite integral. So I'm going to start by factoring out a pi times the integral from -1 to 1 of x to the 4th plus 2x squared plus 1 dx after distributing. And now what I want to recognize is that the integrand is an even function. So instead of evaluating the integral from -1 to 1, I can think about this as 2 pi times the integral from 0 to 1 of x to the 4th plus 2x squared plus 1 dx. So that now when I find the general antiderivative, substituting 1 and 0 in will be a little bit less computational work. So I have 2 pi that I'm going to leave on the outside. The antiderivative is x to the 5th over 5 plus 2x cubed over 3 plus x evaluated from 0 to 1. Well, now I can just think about plugging in 1 because plugging in 0 into the polynomial will just give us 0. So we have 2 pi times 1 over 5 plus 2 over 3 plus 1. And we'll go ahead and simplify this all the way. I have 2 pi, and then I'm going to have a common denominator of 15. So 3 over 15, 10 over 15, and 15 over 15. And that's going to give me 2 times 28, so we're going to have 56 pi over 15. And again, we are finding a volume, so here it would be units cubed. I want to take a second to go back and look at the region that we're rotating and notice that we have symmetry involved, and that if we took the integral from 0 to 1 and found the volume of rotating that region and doubled it, that we would get the same answer, which again is what we did over here when we thought about changing those limits of integration, because this is an even function from 0 to 1, and doubling that particular integral. We would see as an indication to do that as well because of the symmetry involved in the region that we're rotating. In this example, we'll find the volume V of the region found by revolving the area bounded by the y-axis, y equals x cubed, y equals 1, and y equals 8 around the y-axis. We'll start by sketching the region. So here's our region. We have y equals x cubed, and then y equals 1 and y equals 8 are horizontal lines, and the y-axis, and we're rotating this region around the y-axis. So this time our cross sections are going to be perpendicular to the y-axis. So if I think about rotating this, I would have my cross section as a disk that is perpendicular to the y-axis. So here is the radius of my disk that extends from the y-axis to my function y equals x cubed. So my limits of integration are going to have to be from the y-axis are going to have to be y values. So we're going to extend from 1 to 8. So I'm going to set up the volume is the integral from y equals 1 to y equals 8 of pi times my radius squared dy. Well, my radius is going to be obtained doing right minus left. And we have to be in terms of the variable y. So I have to solve here for x. So x is equal to the cube root of y. So I'm going to have the cube root of y minus 0. So I have the cube root of y minus 0, quantity squared dy. So this is the integral that's going to find my volume, and now all that's left is to evaluate it. So I have the integral from 1 to 8 of pi times y to the 2/3 dy. So that's rewriting y to the 1/3 and then multiplying by 2. So I'm going to go ahead and take out the pi and find the antiderivative of y to the 2/3, which is going to be y to the 5/3 times 3/5 evaluated from 1 to 8. So we'll go ahead and substitute in 8 first. So I'm going to have 3 pi over 5 8 to the 5/3 minus 3 pi over 5, 1 to the 5/3. And so evaluating 8 to the 5/3, that's the cube root of 8, which is 2. 2 to the 5th is 32. So 8 to the 5/3 is 32. So we're looking at 3 pi over 5 times 32 minus just 3 pi over 5, because 1 to the any real number is just 1. So here I'm going to have 96 pi minus 3 pi. That's 93 pi over 5. And again, this is a volume, so we'd have units cubed.